Hello, I'm Joe Hamaker. In this presentation, I'll be discussing using learning and rate curves to help us estimate production cost. First, a little bit about me. I'm the director of DoD and NASA programs at Gallerath Federal. I formerly directed cost at NASA, and I have over 40 years of experience with cost estimating and analysis. My email address is at the bottom of the chart, jhamaker@gallerath.com. So I'll be discussing these topics. First of all, terminology. Then I'll refresh us on learning curves. Then I'll show you how to add a rate adjustment to the learning curve formula, and then demonstrate all this in Excel. I'll be using the word learning to mean the classical phenomenon where labor costs per unit comes down as production quantity increases. And I'll be using the term rate effects to mean a slightly more contemporary idea where amortized costs add less costs to each unit produced as the annual production rate increases. And when I say amortized cost, I mean such things as facility costs, standing army costs, that sort of thing. But I'll tell you, there are a lot of terminology issues in the world of learning curves. First of all, there are all these nearly synonymous terms: improvement curves, experience curves, progress functions, productivity curves, dynamic curves, and probably some others. And sometimes these are used to refer to what I'm calling learning, and sometimes they're being used to refer to what I'm calling rate effects, or a combination of the two. By the way, saying something has a steep learning curve, which we often hear to mean difficult to learn, is backwards. A steep learning curve actually corresponds to easy to learn. So let's parse the differences between learning and rate effects a little more. Learning usually refers to labor cost reductions per unit, but sometimes learning curves are used to model other efficiencies beyond just learning. Now, learning curves are always a function of the quantity of items produced, and therefore they're not really sensitive to time. Rate effects, on the other hand, are a function of the annual rate of items being produced, so they are, in that sense, sensitive to time. Now, there are two learning curve theories out there. Both of them predict that costs will decrease by X% every time production quantity doubles. So, for example, a 90% learning curve has costs decreasing to 90% for each of the former costs for each doubling of quantity. You'll see that in a moment. The original learning curve formulation is called the Wright method, also called the cumulative average unit cost method. And there's an alternative called the Crawford method, sometimes called the unit cost method. And then each of the above methods has some other names, which I've listed some of those there. Both approaches use the same equation, y equals ax to the b, where a is the first unit cost, x is the number of units being produced, and b is the learning curve slope. The only difference between the two approaches is Wright defines y to be the cumulative average unit cost, and Crawford defines y to be the incremental unit cost. Also, as we'll see, the Crawford method yields more conservative or higher production cost estimates compared to Wright. So let's get learning out of the way first. Let's do Wright. There's our y equals ax to the b equation, where y is the average unit cost of n units. A is the first unit cost, and you'll also see that called T1, or theoretical first unit cost sometimes. X is the cumulative number of units being produced, and b is the logarithm of the learning curve fraction over the logarithm of 2. So, for example, a 90% learning curve, b equals a logarithm of 0.9 divided by the logarithm of 2, which is a negative 0.1520. Now, Crawford uses the same math, only y equals the cost of the nth unit under Crawford. So let's look at an example given a 90% learning curve, a T1, or first unit cost of 100, and a production quantity of 100. Wright and Crawford use the same y equals ax to the b equation, so yield the same string of numbers that we see there in the table. So the Wright numbers are 100, 90, 84.62, and 81. And the Crawford numbers coming out of the y equals ax to the b are the very same numbers. Now, this is a good time to point out that we start out with the first unit cost of 100. So with a 90% curve, the second unit quantity is doubled. So we see that 90% of 100 yielding the $90 for the second unit. And then when production quantity doubles again to 4, we see 90% of 90 yielding the $81 value there. So Wright declares that these numbers are the cumulative average unit cost, while Crawford declares that these numbers are the incremental unit cost. So to get the Crawford average unit cost, we have to add another calculation in the last column of the table where we average the Crawford numbers. So the first unit cost for Crawford is 100. The second incremental unit is 90. And the average of those two is the $95 value you see there. By the way, back before spreadsheets, and I realize you don't believe it was a time before spreadsheets, but there was. Back in those days, we had to use an approximation formula to get the right average cost. So you don't need to use that anymore. So if you see that crazy formula, just throw it out and use your Excel table to calculate the average for Crawford. Once again, I'll point out that the Crawford average unit cost here are running a little bit higher than the Wright average unit cost numbers. Now let's add that term for rate effects. We're simply going to append another term at the end of the formula. So now our equation becomes y equals ax to the b, r to the c, where r is the annual production rate and c is the rate curve slope. Now note if you're using learning and rate effects, the first unit cost entered for x should really be both a first unit cost, taking into account learning, and a rate of 1 per year. And the usual notation for that learning first unit and rate of 1 per year is a t 1, 1 that you see there. So for example, given a 90% learning curve assumption, and let's assume an 85% rate curve assumption, a first unit cost of 100, and a T11 of 100, and a production quantity of 100 units over 5 years, that's a rate of 20 per year. So first we'll use the Wright theory. We see 100 times the 100 quantity raised to the logarithm of 0.9 over the logarithm of 2. We see the 20 there for the annual rate of 20, production rate of 20, being raised to the logarithm of 0.85 of the logarithm of 2. And when you grind through that math, you'll get an average unit cost of 24.6, which is less than what we were getting taking into account learning only. So this is a good time to point out that R to the C is really a constant term once rate is defined. In other words, the rate effect is going to knock down our T1 cost right at the outset to some lower value than the old first unit cost we had when we were looking at learning only. And then learning proceeds from there. So let's look at all this in Excel. And first, the first two entries up here are learning and rate in green, learning curve percentage and rate curve percentage. I'm actually going to turn rate off for a while by making it be 100%. So let's look at learning only. Here we enter our first unit cost of 100, and here's where we enter our rate of 20 per year, but that's not going to be picked up now. We're just looking at learning. Okay, so on the left side of this table, I have the Wright method being exercised, and we see our cumulative average unit cost coming down from the first unit cost of 100 to 90 to 84.62 to 81, the same numbers we saw before. And over the total quantity of 100 units, we're getting an average of 49.66 from the Wright method, and a total production cost for all 100 units of 49.65. Now, when we use the Crawford method, we get the cumulative average cost per unit coming down from 100 to 95, which we saw this string of numbers before, and then we have to calculate the cumulative average over here in this column. So our total average unit cost under the Crawford method is 58.14, and our total production cost is 58.14 under the Crawford method. Now, watch the numbers in the table decrease when I turn on rate effects. I'm going to assume an 85% rate curve. We see all the numbers go down. For example, our total Wright production cost is down to 24.60, which is about half of what we saw before, and the Crawford method is 28.80. Okay, now you may be wondering, so what are some good learning curve and rate curve percentages to use? Well, good luck with that. Ideally, you have a lot of data from your organization and you can back calculate or calibrate what your experience has been. And I'll pause here for extended laughter since we rarely actually have that data. Alternately, you can research the literature for some recommended learning and rate slopes. Now, my own experience has been to use something around 85 to 95% for learning for aerospace projects, where the lower end of the range, 85%, is used for highly manual operations, where we have a chance for some learning to occur, labor learning to occur. And the higher end of the range is used for more automated or harder tooling operations, where there's less learning. Machines don't learn. For rate curves, I've typically used something around 70% to 85% for the slope for the rate curves. Where the lower end of the range, the 70%, I use where annual amortized cost is expected to be more efficient. So a final word, Gallup is a 75-person company dedicated to providing our customers with best practice cost analysis. Some of our skill sets are listed there. I'll let you look at that for yourself, read that for yourself. Our website is given there. And again, my email address is at the bottom of the chart, jhamaker@galrath.com. Okay, thank you very much.